Welcome everyone to today's edition of Standard Motor Products Power Hour. Our subject today is going to be variable valve timing. So let's get into the material. Our agenda today is going to be understanding variable valve timing, its purpose, and its operation. We're going to identify VVT or variable valve timing common components, and we're even going to put what we learn to use in fixing a car at the very end. Now, what is the purpose of variable valve timing? You may have wondered that. I remember I was a Ford technician. I was a Ford technician for many, many years. I remember back in the late 90s when Ford started implementing variable valve timing on the 2-liter Z-Tech engine. And I literally turned to some of my colleagues, some of my fellow technicians in the shop, and asked them, is this thing designed by aliens? Why do we have this? Well, the fact is we have it for some very good reasons. You know, back in the day when we had fixed cam engines, when that was the only choice, engineers had to do a balancing act between economy and performance. They could tune an engine's camshaft for economy, but then that would be at the sacrifice of power. If they tuned the camshaft for power, it was at the expense of fuel economy and idle quality. So VVT actually gives us the ability to maximize both economy and power. And it's one of the ways that manufacturers are able to get big engine power from a little engine. It actually increases the engine's volumetric efficiency. In other words, it makes an engine breathe better, which can increase engine power, and it allows for a reduction in engine pumping losses. And this contributes to better fuel economy. And it also creates something known as internal EGR. In other words, a variable valve timed engine can actually be manipulated to retain some of the exhaust gases in the combustion chamber, which creates a very efficient EGR effect. Now, what we need to understand what VVT does and what it does not do. It's very important that we establish that. So what we're going to discuss today, of course, being VVT. So we need to understand that variable valve timing changes the timing of the valves by re-indexing the camshaft in relation to the crankshaft. But what it does not do, it does not alter the duration, that is how long we hold the valve open, and nor does it alter the amount that we open the valve. So it doesn't change the valve lift. Now, that's a different system called VVL or variable valve lift, and we're just simply not going to have time in this forum to discuss VVL. We're going to stick with VVT. So as we said, VVT is performed by changing the timing of the camshaft in relation to the crankshaft. Now, we're going to show you the mechanisms that make this work later, but for now, we need to establish a key principle of variable valve timing, and that is, in the case of an engine that has separate overhead intake and exhaust cams, in other words, we have a camshaft that's driving the intake valves and a separate camshaft that's driving the exhaust valves. In that case, the intake cam will be phased toward advance. We're going to advance that camshaft so that those valves, the intake valves, open and close sooner in relation to the piston event. Now, in the case of the exhaust cam, we're going to retard that camshaft. It will be phased toward retard so that those valves will open and close later in relation to the piston event. But in the case of an engine that has the same camshaft driving both the intake and the exhaust valves, that is a single overhead cam or perhaps a push rod cam and block engine, on those engines, we are going to retard. We're going to phase that camshaft in the direction of retard so that all valves will open and close later in relation to the piston event. Now, taking into account that there's going to be some variation in operation from one engine to another, in most cases, the control strategy at idle will be minimal on some engines. In fact, even some engines will have no cam phasing at all at idle. However, the vehicle we're going to look at the very end of this class does phase the camshafts at idle, which is actually going to be part of our diagnosis in that vehicle on that particular engine. But nevertheless, this minimal or no cam phasing is going to result in a smooth engine operation at idle. But now off idle, there's going to be some moderate cam phasing that will take effect, and this will actually result in something known as a scavenging effect. It's actually going to result in in a pull as the exhaust gases are leaving the combustion chamber. We're going to be able to use that force to help draw the incoming mixture into the cylinder, and it's going to actually improve cylinder airflow and engine breathing, which is going to make for a more efficient and powerful engine. This is actually one of the strategies that enables engineers to get big engine power out of a little engine. And as we continue to increase engine RPMs, we're going to be able to become more aggressive with the cam phasing. And that's going to result in reduced pumping losses, increased fuel efficiency, increased fuel mileage, and we're also going to gain that aforementioned EGR effect. We'll call it exhaust gas retention at this point. We're actually going to be able to retain those exhaust gases in the combustion chamber, which will result in better efficiency. Now, there's a number of different variable valve time systems that are out there. We see there's oil pressure actuated, cam torque actuated, magnetic retarder systems, and electrically actuated systems. But for today, we're going to have to focus or concentrate on the oil-driven systems. That's going to be the most common one that you're going to run into. And so for that, we're going to explain, we're going to see our two key components of that system is actually the VVT oil control solenoid and the VVT actuator, also known as the phaser. Now, the oil control solenoid will be duty cycled. The control module will duty cycle a signal to the solenoid to direct a spool valve inside of the assembly. That'll cause a spool valve to move into an appropriate position, which will then direct oil pressure into the appropriate channels that will then feed that oil pressure into the actuator or the phaser. Now, inside of the phaser, we have a mechanism that will allow for the camshaft to be re-indexed in relation to the outer gear as the gear is being driven by either a chain or a belt, which changes the camshaft's relationship to the crankshaft. So let's take a look at the internals of the actuator. So here in the internals, we have a lock pin, as you see, and that lock pin will actually lock that phaser into a home position so that when we shut the engine down, we'll be able to hold that phaser in that position during the next startup event. But once we start the engine, then oil pressure will allow that lock pin to release, and then we'll be able to phase that camshaft. And so the oil pressure will drive the internal veins. You can see these veins, they reside in these chambers. And so depending on which side of those veins we apply oil pressure, we're going to drive those veins in one direction or the other. Now, the camshaft is bolted to the center portion, and that center portion is movable. And so of course, the outer portion being driven by the timing chain or the belt, we're going to change the relationship of the camshaft, again, which is bolted to that center portion in relation to that outer gear. And so how do we control it? Well, when we don't want to phase a camshaft, we are not going to send a command to the solenoid. And so we're going to send it's a 0% command to that solenoid, which will cause oil pressure to be directed into this phaser assembly in the appropriate manner so that we're going to hold that phaser in its home position. But then when we want to phase the camshaft, we want to move it, we're going to send a correct duty cycle command to the solenoid, which will result in that spool valve. Remember, I mentioned that spool valve that is going to, it will cause it to move into the correct position where oil pressure will be fed into these chambers to drive that vein in the appropriate direction and therefore move the camshaft. Now, when the module sees that the camshaft is where it wants it to be via a cam position sensor, we're going to then send the appropriate duty cycle, usually a medium, what would be regarded as a medium percentage duty cycle to that solenoid. And that's going to vary from brand to brand and vehicle to vehicle, what those duty cycle commands will be. But nevertheless, the command will result in holding that cam in the position that the module wants to hold it in. All right, so some considerations when we're doing diagnostics on variable valve timing. We need to remember oil is key. Oil is king. And so we have to be concerned. We will find ourselves concerned with oil level and pressure. We want to always check the oil level to make sure that it's correct. Of course, if the owner of the vehicle is not properly servicing their vehicle, they're going to have problems. Scan data will also be very, very important, as we're going to see at the very end of this session. So again, as we said, oil is king. It's very, very important that we have not just the frequent oil changes, but the correct oil is used. It must be the correct type. It must be the correct weight, viscosity, and it has to be delivered to the system at the correct pressure. If you think about it, we're using oil not just as a lubricant, but we're using it as a hydraulic fluid. So if this vehicle right here calls for 520 oil, we better put 520 in it. We don't want to put 2050 rather in this thing. Just imagine putting 20 or 90 weight gear lube in your floor jack. It's probably not going to work very well. So yes, we have to put the right weight of oil in the engine. In fact, some technicians will, as an early diagnostic step, go ahead and change the oil when in doubt. But all that said, what do you think is going on here? Yeah, we do have that contingency of vehicle owners that are just simply not going to do their proper maintenance. And on a variable valve timed engine, it is especially critical that they do this. Another issue that we've seen that's a common failure, aside from owner neglect, is perhaps maybe a failure with an oil check valve, or perhaps a check valve in perhaps either an oil pump, or perhaps the one that may be mounted in the engine, as in the case of this 1.8 liter GM engine. If we have a failed check valve, it will cause oil pressure issues and therefore cause control issues with variable valve timing. Here's a common failure on a Ford 5.4 liter. Where this seal likes to breach or blow out there on the timing chain tensioner. It causes a loss of oil pressure to the upper portion of the engine where the variable valve timing components are located. In fact, on an engine like this, it is not uncommon to actually see good oil pressure down below, and yet insufficient oil pressure is being fed to the cylinder heads. And so that will cause variable valve timing control issues. And something else that actually occurs very often when you have this problem is that since we have this oil pressure being hemorrhaged behind the timing cover here, we're not properly lubricating the camshaft. And there's a lot of cam bearing failures that you'll see as a result of this right here. Now, I want to show you how understanding the control can help us to diagnose a fault. Now, here we see in this scan data, we see this capture. And you'll notice as the engine speed is changing, of course, the cursor, the numbers over here to the left are reflective of where the cursor is. You can see the engine RPMs changing. So we're operating this vehicle under various conditions, but you'll notice here that the control to the oil control solenoid. Notice what's happening here, and this is an example of a known good. What we see as the module, as the PCM, decides it wants to move the camshaft. He says, okay, it's time to move the camshaft. So he sends a control command to the oil control solenoid, which will result in the spool valve in the solenoid moving to a position where we can move the camshaft. But you notice what happens next. Immediately afterwards, that signal goes, I'll say, fairly horizontal. You notice that? Well, that is actually an indication that the PCM is very happy with where the camshaft is. And he says, stay right there. I want to hold you in that position. And that's what that's horizontal signal right there in the data capture indicates. The PCM's good where that camshaft has landed. He says, okay, stay there. But what about this? What do we have going on here? Well, notice what we have. Here, we have these sloped signals. That's the command to the oil control solenoid. That's an unhappy PCM. He says, hey, you're not where I want you to be. So what does he do? He continues to increase the command to the solenoid. And you can just hear that PCM saying, come on, I know you can do it. I know you can do it. I know you can get there. And does it ever get to the position that the PCM wants it to be? I don't know. But that said, we've got a problem here. It's a control problem. So thinking about this and understanding how the system works, what do you think could be causing the PCM to have this struggle with driving the camshaft to the position that it wants it to go? Could it be low oil pressure? Absolutely. Could it be a bad cam phaser? Yes, it could. Could it be a problem with an oil control solenoid? Certainly. As a matter of fact, as I remember, this particular vehicle that we're looking at this example on actually did have a bad solenoid. That was actually what was causing this. All right, let's put what we have learned to use, and let's fix a car. We have as our subject this 2011 GMC Terrain with a 2.4 liter engine. We got 142,000 miles on this thing. We have a check engine light, and it has a drivability problem. The customer says, well, it stalls out intermittently. So we'll see what's going on. And notice they're traveling. They're open for a quick fix. You can imagine the families in the waiting room. Kids are bouncing beach balls off the wall. They're saying, "Hey, when do we get to go to the beach?" Because they're on their way, and they're having to stop to get this fixed. All right. Well, technician raises the hood, and he actually attempted to pull the vehicle into the shop, and it actually stalled out multiple times going into the shop. So no wonder the customer was motivated to get this thing fixed. Now, once he raised the hood in the shop, he looks around to see if there's anything that looks out of place. He doesn't see anything. There's no family of rodents living under the hood or anything like that. Looking good. So he scans the PCM and he finds this code, P0010, intake cam oil control solenoid circuit failure. All right, well, let's just take a minute and understand what it is that the PCM is telling us. The PCM is telling us that he's looking at this circuit, this intake cam oil control circuit, and he is saying, I see a value on that circuit that I should never see. There's something wrong with that circuit electrically. It's gone open, it's shorted to ground, it's shorted to power. Something's electrically faulted in that circuit. So when you think about what that circuit entails, you have three pieces. You've got a module, you've got a solenoid, and you've got wiring. So we really need to start eliminating those components down to our fault, and we'll find it as we do our diagnosis. So to do this, we're going to need to observe scan data. We want to observe to see what's happening with the VVT operation. We'll say what's happening as far as the command to the variable valve timing solenoid. Then once we do that, we're going to want to test the solenoid and the control circuit. Okay, well, let's do it. Here's our data. A technician using his scan tool starts the engine, and I said it as I said earlier, some engines will have minimal phasing at idle. This one does. You notice here as the idle settles in shortly after startup, the cursor again is going to show us, or the number here to the left rather, is reflective of where the cursor is. So we see the cursor. We see we're running at about 900 RPMs. And during this time, the PCM is attempting to command intake cam phasing. But you'll notice the PID right below it. What is the value that we see? 0. The intake cam is not moving. It's staying in the home position according to the information that the PCM is seeing on the intake cam position sensor. So we're not moving the camshaft, and it kind of looks like the PCM's getting a little frustrated. Looks like she's saying, hey, come on, you need to move, you need to move. It looks like he's kind of hammering that solenoid to say, I need to get something accomplished here. And yeah, he's getting kind of grumpy. But look at the PIDs below that. Notice the exhaust cam. The command is at around 47%. Hey, and you can see that the cam has moved. You can see there, based on the command, that the PCM is issuing to the exhaust cam solenoid. Looks like he's pretty happy with what he sees there. He's satisfied with that, but we have a problem with the intake. All right, well, in our testing now, we're going to pull up a wiring schematics, what our technician did. He pulled up the wiring schematic, and for your viewing, ease of viewing there, I've highlighted the two circuits. You'll see the ECM is represented twice in our schematic. So both circuits come from the ECM. And so the ECM is going to handle both power and ground to that solenoid. And so in our diagnosis, we want to see, is the signal or is a signal getting to the solenoid from the ECM. So our technician is going to connect his graphing meter to that solenoid, to the solenoid circuits. He's going to back probe the solenoid. And so he'll actually see what's happening with the solenoid connected. And with the engine, obviously the engine running, we're going to see what happens. Well, here we go. Now, with his meter in place, he started the engine and he saw this signal from the PCM. I'm going to zoom in on it for you to make it a little bit easier to see. And this tells us what? What do you see here? Well, I mentioned earlier that there will be a duty cycle signal, right? We're going to duty cycle the signal to the solenoid. And what we see on the screen there is a representation of that duty cycle. In fact, you'll notice as the duty cycle is being toggled on, it looks like we're on for a high percentage of each event. Looks like about 80 to 90% of each event as we're toggling that signal to that solenoid, which tells us that the ECM wants to move the camshaft. He's trying to energize that solenoid to make something happen. But it also tells us what else? It tells us the signal is getting to the solenoid. So could you say that, remember I mentioned three pieces to the equation? We have a module, we have wiring, and we have a solenoid. Could we now at this point say that we could eliminate the module and the wiring? That sounds good, right? Sounds right. It looks like we need a solenoid. But just to go ahead and further verify, the technician performed an ohm test. He's going to check the resistance across the windings of the solenoid. Inside that solenoid, of course, we have those electrical windings that produces that magnetic field that makes everything work in the solenoid. Well, when he checks the resistance of the solenoid, he finds we have 132 ohms of resistance. Now, how do we know if that's good or bad? Well, specifications and service information says you should be between 8 to 15 ohms. But you know, if you don't have a specification and service information that you can readily access, we have a solenoid on the other side, the exhaust side. Couldn't we compare it against that if we needed to? And the answer is yes, we could. Well, this technician didn't need to. He had the spec from service information and he knew that it was faulty. We need a solenoid. But given the fact that these engines, and it is a pattern failure with these engines, given that fact, knowing that they have a high failure rate, the technician actually recommended that we go ahead and replace both. Let's replace both the intake and the exhaust solenoid. They're not that expensive. They're fairly easy to access, and it wouldn't be very prudent to leave it go out the door with a chance that the other solenoid could fail even before the family gets back home. So we're going to go ahead and replace both solenoids. And that said, here is our fixed data. Now, remember what it looked like before. You remember we had the PCM very angry. He was pretty upset that that solenoid or the camshaft wasn't moving per his command. But now what do you see? Well, where the cursor is, we have a good, nice, steady signal, and it looks like that PCM is very, very happy with what it sees. All right. With that, we appreciate you joining us for today's class. This class was actually an abbreviated session that represents the quality training that we offer at Standard Motor Products. So I'd like to direct you to our YouTube channel, Standard Brand, at the Standard Brand YouTube channel for further information and for more training. And as always, make sure that you see your parts representative for quality Standard Motor Products aftermarket parts. Thank you for attending today, and we'll see you next time.